Alright, welcome back everybody. In this video we're going to look at the alternating series test and how we use it to show the convergence or divergence of alternating series. You see the alternating series test outlined here at the top of the screen. And realize when we're talking about this, we've got this alternating term, the -1 to the n plus 1, or any other alternating piece that we might choose to write it as. But it's everything else that we're going to use to determine if the alternating series converges or diverges. Once we eliminate the alternator from our thought process, as long as this green highlighted u sub n is always positive, as long as u sub n is greater than or equal to u sub n plus 1 for all values of n greater than some particular integer, we usually don't have to go too high with that integer to find where it starts to be greater than or equal to u sub n plus 1. And as long as the limit as n approaches infinity of u sub n approaches 0, this alternating series will converge. And so basically when we're using the alternating series test to determine if an alternating series converges or diverges, we're just going to go through these three steps, kind of like a little checklist. And if we find that all three of them are true, then the series converges. If we find that any of the three are false, then we know that the series diverges. Alright, so let's look at this first example. And I need to look at everything other than the alternating series term. So in reality, for this example, our u sub n that we're looking at is the function 1 over n. So we ask ourselves, first, is u sub n greater than 0 for all values of n? And if you think about all these positive values of n, 1, 2, 3, 4, 5, 6, for all of those, u sub n is greater than 0. So that does indeed work. Step 2. Is u sub n greater than or equal to u sub n plus 1 for all values of n above a certain starting point? Well, let's start with, say, 2. Is 1/2 greater than 1/3? Yeah. And 1/3 is greater than 1/4, and 1/4 is greater than 1/5, and so on and so forth. So that statement is true for all values of n. And then the last part, does the limit as n goes to infinity of u sub n, does that approach 0? And if we think about that for u sub n equals 1 over n, as n goes to infinity, u sub n indeed does approach 0. So we've passed all three terms in the checklist, and therefore this first series that we looked at converges. Alright, let's go on to example 2. So, and realize we don't necessarily need to do the items from this checklist in order. If we can find that any of them are false, that means that the series diverges. So, go through these thought processes. And so I identify my u sub n. In this case, it's n squared over n squared plus 5. Is that positive for all values of n, natural numbers? And yes, it is. This is positive for all those, so it passes that test. Now I'm going to jump right to test number 3 here. Instead of investigating the values of these, the limit as n goes to infinity of u sub n here, you should recognize that the limit as n goes to infinity of this fraction, with n squared in the numerator and n squared plus 5 in the denominator, you should recognize that as n goes to infinity, that in fact approaches 1. And so we've violated the third step, and therefore we know that this particular series diverges. Okay, on to example 3. Again, we have a slightly different alternator, but it still works the same. And so we're going to look at the u sub n portion of this. U sub n is equal to square root of n over n plus 4. Alright, and so we want our three things to take place. We want u sub n to be greater than 0. We want u sub n to be greater than or equal to u sub n plus 1 after some starting point. And we want the limit as n goes to infinity of u sub n to be equal to 0. And so we think about this with this particular u sub n. Is u sub n always greater than 0 for the natural numbers n? And it is. So it passes that one. And then let me see. I'll think about step 3 next. Does the limit as n goes to infinity of u sub n equal 0? Yes, because the power in the denominator of n is greater than the power in the numerator. So it indeed passes that test. So then we need to decide, is there a value of n where from that point on u sub n is always greater than or equal to u sub n plus 1? And to do this, I'm just going to investigate a little bit. I would just substitute numbers in my head, but with the square root here, it gets a little cumbersome for us to think about this. So I'm going to use my calculator as a tool to help me out. I type in, the u sub n, and I'll set up a table, and we'll start at 0. And so I look at my table, and I look at these y values, and it looks like they're getting bigger here in the start. But then once we hit n equals 4, from that point forward, all of those u sub n values, u sub n is bigger than the one that follows. And so this is true for n greater than or equal to 4. So we passed the third test. And so this series converges. Okay. On to example 4. Again, we're going to go through our checklist. We first identify u sub n. Now realize that this piece right here, cosine of n pi, that's just an alternator, just like the quantity -1 to the n. Cosine of the quantity n pi, as we cycle through the natural numbers n, it just bounces back and forth, cosine of pi, cosine of 2 pi, cosine of 3 pi, etc., etc. And those values alternate between -1 and +1. So that's just another form of the alternator. And so our u sub n here is 1 over the square root of n. And so we're going to run this through our checklist of things that need to happen. Okay. Is this positive for all natural number values of n? Yes. Does the limit as n goes to infinity of u sub n equal 0? Yes. And then is u sub n greater than or equal to u sub n plus 1 for all the values of n beyond a certain point? Is 1 over the square root of 2 greater than 1 over the square root of 3? Is 1 over the square root of 3 greater than 1 over the square root of 4? 1 over the square root of 4 greater than 1 over the square root of 5? And I don't even need to really use my calculator here, since the denominator is getting successively bigger in the n plus 1 terms. That means that the entire fraction is successively getting smaller. And so indeed, it does pass that third check. Oops. And so, this series converges. Alright, that's where we're going to stop today. We'll come back for the rest of the examples from this lesson. See you guys next time. Have a great rest of your day.